This is AP Calculus AB, and in this video, I'm going to talk about section 4.3, derivatives of inverse trig functions. And also, there's one other derivative rule that we're going to cover in this section that really isn't covered in your book in depth, and it is just the derivatives of general inverse functions. And that's really what we're going to start with here. So what I have graphed on the screen are two functions, x squared and square root of x. And if you think about that, g of x is the inverse of f of x. It's the inverse function of f of x. So when we say functions are inverses, just as a kind of review from Algebra 2, if I have a value that I plug into f of x, so let's say, for instance, the point that's plotted there, the point 2, 4. When I plug 2 into the f function, I get an output of 4. Okay, so if I have an inverse function, the reverse should happen. So if I take the output from the f of x function and plug it into the inverse, I should get the number that I originally started with. And you notice here, if I plug in x is equal to 4, I get an output of 2. So that's what we're looking at when we're talking about inverse functions. The other thing to remember is that when I have a function and its inverse, they are reflections over the line y equals x, or you can think of it as the x and the y coordinates switch places. Okay, so what we're going to do here is look at some patterns and figure out what the derivative rule is for a function and its inverse. So we're talking about f prime and g prime. So first of all, I'm just going to write this here. F prime of x obviously is just going to be 2x. So that's pretty simple. And then for g prime, that would be 1 over 2 root x. Okay, so let's take a look at these derivative values. So f prime at 0 would obviously be 0. G prime at 0 would be undefined. And you can see because I would be dividing by 0. Okay, let's look at the next pair. F prime at 2 would be 4. And then notice the corresponding at g prime at 4, I'm actually going to get 1 over 2 times the square root of 4. So 1 over 2 times 2, or 1/4. And then the last pair of points we have here, f prime at 4 would be equal to 8. And then g prime at 16 would be 1 over 8. Now there's a relationship between these pairs of derivatives that I have here. And that's really what we're looking for. So the main thing to remember when we're talking about a function and its inverse is that the derivatives at corresponding points are going to be reciprocals of each other. And if you think about what I mentioned a minute ago about the whole idea that when I have a function and I look at a point on a function, and if I look at the corresponding point on the inverse function, the x and the y coordinates switch places. So that's essentially what happens here. So if you think about in my f primes that I have here, that would be the change in y over the change in x. Well, when I switch the x and the y coordinates, that means I'm going to have to flip that slope to get the corresponding slope for the inverse function. So if you think about, for example, if I have at 0, 0, I have a slope of 0. Well, the corresponding point on the g function is 0, because if I plug 0 into x squared, I get an output of 0. Okay, so if I think about a horizontal slope, well, the reciprocal of that would just be a vertical slope. Same thing here. The point 2 on the f function corresponds to the point 4 on the g function, because 2 plugged into the f function gives me an output of 4. And notice the relationship between the slopes. I have a slope of 4 for f prime at 2, and I have a slope of 1/4 for g prime at 4. And again, the x and the y's are switching places, so I'm just taking the reciprocal of the slope to get the derivative for the new function. And then the same thing at f prime at 4 and g prime at 16. Those are corresponding points. So the slope of 8 for f prime of 4 corresponds to the slope of 1/8 for g prime at 16. Now there is actually a rule that you can follow for this. I don't usually try to memorize the rule because I think it makes it more difficult than it needs to be. But let me show you where this rule comes from. This is saying that if g is the inverse of f, then the derivative of g is equal to 1 over f prime at g of x. So when we have inverse functions, and you may or may not remember this from Algebra 2, but if I take the composite of those two functions, that should give me x. Well, where this derivative rule comes from is just taking the derivative of that expression. So that's our definition of inverse functions. If I take the derivative here implicitly and solve for g prime of x, I'll get that derivative rule. Okay, like I said, I don't recommend memorizing the derivative rule because I don't think it's necessary. I think if you can remember the way that the derivatives are related to each other at corresponding points, it becomes pretty simple. Okay, so notice what it says here. Inverse differentiable functions have reciprocal slopes at corresponding coordinates. So for example here, we're looking at f prime at 5, and we know that it's equal to 10. Well, this question over here says g prime at what would be equal to 1/10? Well, the reciprocal of 10 is 1/10, so that means that I should be at a corresponding point on the g function. Now remember, the f function was x squared. If I plug 5 into the f function, it gives me an output of 25. So that means that when I'm referencing the corresponding slope on the g function, I should be looking at x is equal to 25. So g prime at 25 would be equal to 1/10. And you can check that. If you go back up here, if you plug 25 in for x into this derivative, you can see that you're going to get 1/10. Okay, so this is something that we don't use this derivative rule a lot, but it is something that tends to show up on the AP exam, and that's the reason that I wanted to spend a little bit of time covering it. For whatever reason, the College Board tends to put this derivative rule on the AP exam, and we rarely use it in class, if ever. But we do practice it just so that if it does show up on the AP exam, you've seen it. So this is an old AP exam question. Let f and g be functions that are differentiable everywhere. If f of g of x is equal to g of f of x is equal to x, and remember, we talked about this a minute ago. That's just establishing that g and f are inverse functions. And then it says if g of negative 2 is 5 and f prime at 5 is negative 1/2, what's g prime at negative 2? Well, remember, this point that they gave me here is really the key to the whole problem, because that tells me that negative 2 on the g function corresponds to 5 on the f function. So if I know the derivative of at 5 on the f function, I know the derivative at negative 2 on the g function is just going to be the reciprocal, so this is going to turn out to be negative 2. So there's literally no work involved on this problem. It's really just understanding what's happening when I switch those x and y coordinates is forcing me to take the reciprocal of the slope when I'm looking at a corresponding point on an inverse function. All right, so the rest of what we're going to talk about here are the inverse trig derivative rules. And as we go through these, you are going to see some trig identities that you're going to have to use from time to time to do a little bit of simplifying. So don't forget our Pythagorean identities. I don't memorize all three of these. This is the only one I know off the top of my head. Sine squared plus cosine squared is 1. If I ever need the other of the three trig identities, all I do is just divide by whatever I need to divide by to get it in that form. For example, for this one, you can see the first term is a tangent squared. That means if I go back to that original form and I divide everything by cosine squared, then you can see you'll get tangent squared plus 1 is equal to secant squared x. Okay, so just keep those in mind as you work through the assignment, because you will see some simplifying where you might have to do a little bit of work to get things into certain forms. Okay, so let's talk a little bit about these derivative rules and where they come from. So now that we know implicit differentiation and the chain rule, we actually have the ability to come up with as many derivative rules as we want. And this is an example of creating one. You don't have to know how to do this. I just wanted you to see it so you understand where it comes from. So we're trying to find the derivative of the inverse sine of x. Right now, we're going to assume we don't know a rule for inverse sine of x. So what we're going to do is rewrite this equation in a form where we can take the derivatives. So I took the sine on both sides, and that gave me sine of y is equal to x. And now I can take the derivative. So I'm just going to take the derivative on both sides with respect to x, and that gives me this. Cosine y dy dx is equal to 1, and then solve for dy dx, and I get 1 over cosine y. Now, what's tricky is you might look at that and go, well, how did they get to this from 1 over cosine y? Well, where it came from is you just have to draw the right triangle that would represent that situation. So if I'm saying cosine y, that means my angle is y. This is a right triangle. And cosine is equal to 1. So what that's telling me is that if I put an x here, then I also know that this would have to be a 1. And the reason that I know that is because I have this relationship that we established back here at the beginning. The sine of y has got to be equal to x. Well, here's my angle of y. You can see the opposite over the hypotenuse is now equal to x. So I've created a right triangle that's representing the constraint that I have with this equation. Now, there is a third leg here that we could find using the Pythagorean theorem. And the length of this leg, remember the hypotenuse is 1, so I could do 1 squared minus x squared and then take the square root. So basically 1 minus x squared inside the square root would be the length of that third leg. And now think about the cosine of y. Well, the cosine of y would be equal to the square root of 1 minus x squared over 1. This has 1 over cosine y, so I just take the reciprocal of that and get 1 over square root of 1 minus x squared. So that's where the derivative rules come from for the inverse trig functions, just doing those similar operations for inverse sine, inverse cosine, inverse tangent, and so on. Okay, so there are 6 rules here. And this is going to look a little bit overwhelming at first, but it's not nearly as much as it first appears. And I actually have 12 rules shown here, but you really only need to know 6 of them, and in the end, it's really 3 of them. So look at the way that these are lined up. And you can see I lined them up this way on purpose because there's a relationship between these. So look at inverse sine and inverse cosine, that pair. So with that pair, the derivative rules look almost identical. Inverse sine is 1 over the square root of 1 minus x squared. Inverse cosine is negative 1 over square root of 1 minus x squared. And again, we could derive the derivative for inverse cosine the same way we did inverse sine. I'm not going to show all of those, but you can find it the same way. So notice that those are a pair. So really, if I can remember which ones are paired up, I really only have to remember 3 of these. For example, look at inverse tangent and inverse cotangent. Derivative of inverse tangent is 1 over 1 plus x squared. Derivative of cotangent is negative 1 over 1 plus x squared. And then the same thing for inverse secant and inverse cosecant. We have a positive 1 here, and we have a negative 1 there. Otherwise, the derivative rules look the same. Okay, so that's one way to remember the rules, and that's typically how I remember the rules. But also keep in mind, if your argument for your trig function, your inverse trig function, is not just x, then the chain rule comes into play. And that's what this next set is showing you. So it's the exact same rules, just taking into account that if that argument for the inverse sine in that case, if it's a u, then I'm going to have to multiply by du dx. Okay, so just don't forget to use the chain rule when it's appropriate. All right, so I want to show you one of these, and then I'm going to have you work through some example problems and check over your answers. So the main thing here is sometimes the algebra and simplifying these can be a little bit tricky, but the rules themselves are very, very straightforward. So let's do the derivative of the inverse sine of x over 2. So the first thing is you have to remember the rule. The derivative of inverse sine is 1 over the square root of 1 minus x squared. Well, I don't have an x here. I have an x over 2. So really, I'm thinking about this with the chain rule. So I'm going to do 1 over the square root of 1 minus x over 2 squared. So that's the derivative of the outside times the derivative of x over 2. So that'd be times 1/2. Now, that's the derivative. At this point, I'm going to do some algebra to simplify. So I'm going to rewrite this as 1 over the square root of, or really 2 times the square root of 1 minus x squared over 4. Now, that is the derivative, but that's really not in a nice simplified form because right now I've got an improper fraction. So typically we're going to want to simplify a little bit more than this. Now, notice within that denominator and what's inside the square root, I could get a common denominator. And I'm going to rewrite this as 1 over 2 times the square root of, 1 is the same as 4 over 4, so 4 minus x squared all over 4. And now I can simplify this down a little bit. And if I were to take this 4 out of the square root, it would give me a 2 in the denominator. So essentially I would end up with a divided by 2 when I take that out. So what happens then is this simplifies down into 1 over the square root of 4 minus x squared. So sometimes with these, when you take your derivative and you're looking at, for example, on a multiple choice, you're looking at your answer choices, or you're looking in the book and checking your answer in the back of the book. When you see questions that your answer doesn't match the form that they have, make sure you check the algebra and see if there's any way to manipulate your form to match up with the form that's there. So in this case, when you got to this point, you know, if it was a multiple choice, you might look at the choices and you might think, there's no way that 1 over square root of 4 minus x squared can be my answer. But the reality is, with a little bit of algebra, we can make that form of the solution show up. Okay, so what I want you to do here is go ahead and work out these next 5 questions, just all inverse trig derivative rules. If you need to go back and look back at the table that I gave you of all of the rules, go ahead and do that. But you'll see that some of these, there's not a lot of simplifying, and then other ones, you might have to do a little bit of simplifying. So pause the video, and when you come back after you work these out, I'll show you the solutions. Okay, so here are the answers that you should have come up with. The first one for inverse cotangent of 6x. So the rule is -1 over 1 plus u squared du dx. And you can see in this case, the only simplifying I did was multiplying the 6 to the -1. For the next one, inverse tangent of 3x, it's 1 over 1 plus u squared times du dx. So again, not really a ton of simplifying to be done there. Inverse cosine, I've got, in this case, inverse cosine of x squared. So it's -1 over the square root of 1 minus u squared du dx. In this case, I didn't have a rational expression as my argument for the inverse cosine, so I don't have to do all of that complex fractions simplifying like I had to before. And this one, again, simplifies down pretty nicely. Now, this is where they get a little tricky. I have an inverse secant here, inverse secant of x squared. So when I'm taking the derivative here, it's 1 over the absolute value of u times the square root of u squared minus 1 times du dx. Now, notice we have an x squared inside of an absolute value. X squared is always going to be positive. So I can take the x squared out of the absolute value, and you can see down here, now that allows me to cancel the x out with the x that's in the numerator, and we've got a simplified form that looks like this. The main thing to remember when you're simplifying with the absolute values, anytime you have an even powered exponent, you can take it out of the absolute value. All right, similar type of question here, we have inverse cosecant. So it's -1 over absolute value of u times the square root of u squared minus 1 times du dx. And this one, there's not really a lot of simplifying to be done, so it's pretty straightforward. Now, when you are trying to remember on these derivative rules, notice how we have these expressions, 1 minus x squared here, and we have an x squared minus 1 there. The most common mistake that people make with these derivative rules is they can't remember if the x comes first or last. And what I do to remember the order is I always remember that for an inverse secant, notice the location of the x terms here. The x terms are essentially next to each other in the expression. So I know the x squared comes first in the inverse secant, and then I just know that inverse sine is opposite of that, 1 minus x squared. So you can use that as just a little trick to use to try to remember which way to set up the 1 minus x squared versus the x squared minus 1. All right, so I've got a couple more problems here that I want to show you. The next one, it says, find the equation of the tangent to the graph of y is equal to inverse tangent of x at the point where x is 2. This is actually a really simple question, but I want to show you when you work this out how I would expect your answer to look. So when you take the derivative here, because obviously we need a tangent slope, it would be 1 over 1 plus x squared. When I evaluate that at 2, I'm going to get 1/5. So there's my tangent slope. The other thing I need is I need to know what is the point that this line has to go through. Well, when x is 2, I have a y value of inverse tangent of 2. Now, you might be tempted to plug that into the calculator and get a decimal approximation of inverse tangent of 2. It's better to leave your answer with the exact solution. So think of inverse tangent of 2. It's an irrational number. It's like pi. So if I have an answer where I know there's a pi in it, I write it as pi, because then that way I don't have to try to cut off the decimal knowing that pi goes on forever. So we're going to write this as inverse tangent of 2. So for the equation of the line, y minus y1 would just be y minus the inverse tangent of 2 is equal to my slope, which was 1/5, times x minus 2. And that's how I would want you to write your solution. So it looks a little bit weird because we have an inverse tangent within the equation of the line, but remember it's because it's an irrational number. So you just have to get in the habit of leaving things in that form so that you have those exact solutions as opposed to plugging into the calculator and getting an approximated solution. All right, so there are two questions here that are going back to that first rule. The first rule that we talked about where the derivative of an inverse is the reciprocal of the derivative of the function at the corresponding point. So there's two problems here, and it's just really, it's notation, and it's also just practicing with that rule. The first one says take the derivative of the inverse of f at 3. The second one, notice it says f inverse, so it's the inverse prime, which is just the derivative of the inverse at 4. So use the values in this table and see if you can figure out what the solutions are. And when you unpause the video, I'll show you the solutions. Okay, so here's what you should have ended up with. The main thing is we have to know what points are corresponding here. So we're looking at the inverse at 3. So what I'm doing when I look at this table is I'm saying, okay, on my original function, where on my original function do I get an output of 3? And if you notice here on this point, right up here, I've got, if I plug 5 into the f of x function, I get an output of 3. So that means that when I'm looking at the inverse function, I need to be looking at the derivative of the original function at 5. Okay, so what I did was then I looked at the table and said, okay, what's the derivative of the original function at 5? Well, it's right here, it's -2. So knowing that to be the case, if I want the derivative of the inverse at 3, then all I have to do is take the reciprocal of that corresponding point. So the reciprocal of -2 is -1/2. Okay, so same idea on the second problem. You can see we're looking at the inverse evaluated at 4, the derivative of the inverse at 4. So again, I'm looking on this table and I'm thinking, okay, where is the original function giving me an output of 4? And you can see here, when I plug in 1, I get an output of 4. So that means 1 on the original function corresponds to 4 on the inverse function from the perspective of the derivatives. So I got the derivative of the original function at 1 to be 3. And now I know at the corresponding point, the derivative is just going to be the reciprocal. Okay, so all of these derivative rules are relatively simple. It's just a matter of practicing with them enough that you've really got the rules down and you don't have to stop and think about them every time that you see them. When you look at these rules, I will just tell you right away, the two that we are going to use the most are the rules for inverse sine and inverse tangent. We'll use the other ones from time to time, but inverse sine and inverse tangent are primarily the rules that we're going to see in this class moving forward. So definitely make sure you know all 6 of them. But, you know, like I said, in the end, you're very unlikely to see those other 4 except in rare circumstances.